Welcome to our guide on basic data analysis and visualization using EViews. This presentation will focus on mastering the fundamental building blocks of EViews, its objects. We will journey from understanding individual variables, known as univariate series, to visualizing complex multivariate relationships on geomaps. The core message is that data, in its raw form, is just a collection of numbers. Our goal is to transform this data into a compelling economic story.
Raw spreadsheets, like the one on the left, are often overwhelming and hide the underlying story. They are voluminous, messy, and silent. To make sense of this, we use structured EViews objects. For individual variables like wages or CPI, we use a series object. To analyze the relationships between multiple variables, such as how wages and inflation move together, we use a group object. Ultimately, our goal is to make the data speak, revealing patterns, relationships, and distributions that are not obvious in a simple table.
When you start your analysis, the first question is always, what is your data structure? This decision map helps you choose the right tool for the job. If you're looking at a single variable, like inflation over time, you're doing univariate analysis. The correct tool is a series object, which lets you create histograms or calculate descriptive statistics. If you're examining multiple variables together, such as the relationship between GDP, consumption, and investment, you're doing multivariate analysis. Here, you should use a group object. For data with a geographical component, like unemployment rates by state, the geomap object is the perfect tool for visualization. Finally, if you need to compare data across different categories, such as wage differences between union and non-union workers, you'll use a categorical graph. The series is the fundamental unit in EViews, the atom of your data. It holds a single column of data, which can be time series or cross-sectional. Its most common views are the spreadsheet and the line graph. A group is essentially a collection of series. It's important to know that a group does not store the data itself. It only holds references to the series. This makes it a powerful tool for multivariate analysis, like testing for co-integration, estimating VARs, vector autoregressions, or examining correlation matrices. Geomaps are specialized for geographic visualization. They work by linking data from your EV series to external map files, called shapefiles, .prj. This requires a key attribute, like a state name or country code, to match the data row to the correct map shape. Descriptive statistics are fundamental for summarizing the main features of a dataset. We categorize them into measures of central tendency, dispersion, and shape. Central tendency describes the typical value, including the mean, calculated as the sum of observations divided by their count, and the median, which is the middle value in a sorted dataset. Measures of dispersion describe the spread of data. This includes variance, which is the average of the squared differences from the mean, and its square root, the standard deviation. The shape of the distribution is described by skewness, which measures asymmetry. A skewness of 0 indicates a perfectly symmetric distribution. Kurtosis measures the tailedness or peakiness of the distribution, with a value of 3 typically associated with a normal distribution. Finally, the Jarque-Bera, or JB, test statistic combines skewness and kurtosis to formally test for normality. If the JB probability is less than 0.05, we reject the null hypothesis, concluding that the data is not normally distributed. This math logic helps us understand the underlying distribution of our data. When analyzing data, we must be aware of underlying assumptions. First, normality is key. Many economic variables, like income or wealth, are naturally skewed. If our data is heavily skewed, we might need to apply a log transformation to make it more symmetric, which is crucial for many statistical models. Second, for time series data, stationarity is crucial. A non-stationary series, one with a clear trend, can lead to spurious correlations, finding a relationship where none truly exists. We need to ensure our series have a flat mean over time. Third, Categorization allows us to split data into subsets for comparison. We can use categorical variables, often coded as 0 or 1, to analyze things like wage gaps between different groups or regional economic differences. A critical point to remember in economic interpretation is that correlation does not imply causation. A group analysis might show that two variables move together, but it doesn't tell us if one causes the other. This slide summarizes these important considerations for sound economic analysis. This slide covers two key concepts, binning and linking, along with specific techniques. Binning involves grouping continuous data into discrete ranges, which is essential for categorical analysis. We can perform binning using quantile bins, which ensure an equal number of observations in each category, or value bins, which create categories with equal interval widths. For geomaps, linking is the process of associating map shapes stored in shapefiles with your EViews data series. This is done by matching a key attribute, like a state abbreviation, between the shapefile and your data. Shapefiles themselves are external geographic data files, often sourced from entities like the Census Bureau or created with GIS software like ArcGIS. Let's quickly go over the menu paths for common tasks. To analyze a single series, you first open the series, then go to View, Descriptive Statistics and Tests, Stats table. For multivariate analysis, you first create a group. Then open the group and go to View, Graph to create plots like line graphs of all series together. To create a geomap, it's a bit different. You go to the main menu and select Object, New Object, and then choose Geomap from the list. Here's a great shortcut. To quickly create a group, select multiple series in the Workfile window, right-click, and choose Open as Group. This is much faster for instant multivariate analysis. And remember, almost any graph in EViews is editable. Just double-click on the graph to open a Properties dialog where you can change colors, labels, and much more. When creating categorical graphs, EViews asks you how to use your factor or categorical variable. You have two main options, within graph and across graph. Choosing within graph, as in scenario A, plots all categories on the same set of axes. This is ideal for directly comparing levels or values. For example, plotting male and female wages on the same bar chart makes the wage gap immediately obvious. Choosing a cross-graph, as in scenario B, creates a separate individual chart for each category. This is best when you want to compare the shape or distribution of the data for each category, such as comparing the histogram of wages for men versus the histogram for women. The first step in our analysis is to prepare the data and analyze individual series. We start by inspecting the wage series from our CPS data. The histogram shows clear positive skewness, which is typical for income data and suggests the presence of outliers. The descriptive statistics confirm this, with a skewness value of 1.85 and a Jarque-Bera test probability of 0.0000. This low p-value leads us to strongly reject the null hypothesis of normality, indicating that the wage data is non-normal. This finding is crucial, as it suggests that a log transformation of the wage variable might be necessary for more accurate regression analysis later on. After analyzing the overall wage distribution, we now want to compare wages based on a specific characteristic. We'll use the union factor, a categorical variable that is 1 for union members and 0 otherwise. By creating a categorical graph of the median wage by union status, we can slice the data and uncover patterns hidden by the overall average. The visual insight is immediate and powerful. The bar for union workers is significantly higher than for non-union workers. This reveals a substantial union wage premium that was not visible in our initial analysis. While the overall median wage was $19,000, this categorical graph might show that the median for non-union workers is closer to $18,000, while the median for union workers is over $25,000. This is a key insight that simple averages would completely miss. We've compared wages based on one category, but economics is about the interplay of multiple variables. Next, we'll use a group object to analyze several variables at once.
Now we move to multivariate analysis using a group object. Here, we've grouped 3 time series variables: GDP, gross domestic product, M1, money supply M1, and the interest rate. The line graphs show the behavior of these variables from 1980 to 2020. We can see that both GDP and M1 have a strong upward trend, while the interest rate has a downward trend. The correlation matrix quantifies the linear relationships between these variables. As expected from the graphs, the correlation between GDP and M1 is very high at 0.95. This high correlation is a red flag for multicollinearity. If we were to include both GDP and M1 as independent variables in a regression, this strong linear relationship could destabilize our coefficient estimates. Group analysis is essential for diagnosing such issues before modeling.
Our final analytical tool is the geomap, which helps us visualize data with a geographic dimension, such as unemployment rates by state. Geomaps are incredibly effective at revealing spatial autocorrelation, the tendency for values in nearby locations to be more similar than values in distant locations. This is a pattern you would never see in a spreadsheet. On this map of unemployment, we can see a clear concentration of higher rates, darker colors, in the Northeast and Midwest, while the Great Plains states have lower rates, lighter colors. This spatial pattern prompts new questions about regional economic policies or industry concentrations. The core technique here is linking, which connects the where, the map shape from the shapefile, to the what, the data value from your series.
On this slide, titled Interpretation and Diagnostics, we bring together the insights gained from our various analyses. Our univariate examination of wage data, depicted by the histogram, revealed a clear right-skewed distribution. This is a crucial diagnostic, suggesting that a log transformation might be necessary for more robust modeling. Moving to bivariate analysis, the bar chart effectively showed that union membership correlates with higher wages, providing an initial interpretation of a union wage premium. In our multivariate analysis, the correlation matrix highlighted a strong correlation between M1 and GDP, signaling a potential issue of multicollinearity in regression models. Lastly, our spatial analysis, visualized through the geomap, demonstrated that economic distress is not uniformly spread, but is regionally concentrated, offering important geographical context. On the right side, the story emphasizes that we successfully transformed raw numbers into a coherent narrative. This was achieved through a logical progression, starting from the distribution of individual variables, moving to category comparisons, exploring complex comparison and multivariate relationships, and finally adding vital spatial context. Each step, utilizing different EViews objects, contributed a new chapter to our comprehensive economic story.